Hello, my name is Minchul Kim, and in this presentation, I will be discussing our paper, KeyPoint Relative Position Encoding for Face Recognition. This paper is presented in CVPR 2024. Let's take a look at each component. Let's start with a vision transformer. In this diagram, we want to highlight the multi-head attention module inside. Specifically, multi-head attention computes the attention score matrix, which is QK transpose. Previous works have shown that adding relative position encoding, RPE, helps the model learn better by injecting prior information, such as relationships between nearby pixels are more important than those between distant pixels. The addition of RPE to the attention score is shown in these equations. For each QK pair, we compute a scalar term Bij that is added to the original term before normalization. But what exactly is this term Bij? Bij is a learned value for unique query and key location pairs. For example, B12 is a function of the location of query 1 and key 2, and B34 is for query 3 and key 4. Note that the function takes the locations as input, not the features themselves. So a suitable function could be the distance function, such as the Euclidean distance. With all pairs of query and key, we create a B matrix that has the same shape as the attention matrix. However, for regular RPEs, the issue is that the query-key relationship is the same for all images, regardless of their content. Let's illustrate this with an example. Consider these three images with different content. One is a scaled and translated version of another, and the last one has a different pose. RPE considers all combinations of query and key. For the highlighted pair, we see that the corresponding content in each image differs. This RPE is good enough to inject prior information, such as the fact that nearby pixels are globally important, but it is not sufficient to control importance based on the semantic content. Therefore, in this work, we address the static nature of RPE and propose a dynamic RPE that is both efficient and content adaptive. The high-level overview of our proposed solution is to compute additional keypoint information from an image and incorporate it when computing the RPE. This illustration shows that a keypoint gives additional information on how to modulate the relationship between query and key. We call this KP-RPE. Specifically, for a given query, we compute the distance to all keys. This is equivalent to normal RPE. We take the distance function from IRPE and use the quantized distance. The animation shows the quantized distance computed for all keys from different query points, indicated by a star. The same color implies the same distance. Next, we optimize what actual value each color or distance should represent. For instance, purple could be 0.5 and blue 0.2. We formulate this as a linear function of the distance between the key point and the query. In other words, the static value dictionary for RPE becomes a function of key points. Then, for each query key pair, the actual value depends on both the distance between the query and key and the location of the key points. We define key points as a set of points that provide clues about the scale and translation of an object. For example, face datasets can use facial landmarks as key points. For gait recognition, body skeleton points can be key points. For the MNIST dataset, we can convert the maximum cover box into 4 corner points and use those as key points. We demonstrate the efficacy of our proposed KP-RPE in face recognition. For challenging benchmark datasets such as TinyFace and IJBS, we show significant performance improvement and achieve state-of-the-art results. We also apply KP-RPE in gait recognition models, using body skeletons as key points. We observe meaningful performance gains. KP-RPE brings performance improvement by introducing a fine transformation robustness to the model. In this experiment, a model is trained on the MNIST dataset and tested on an affine transformed version of the MNIST. Compared to previous methods for position encoding, such as absolute position embedding or IRPE, KP-RPE shows significant performance improvement, indicating that KP-RPE is more robust to unseen geometry. The second row, ABS-PE star, represents a method that draws key points onto the image. This method does not bring in a fine robustness, demonstrating that the way in which key points are used is important. We believe that KP-RPE's linear relationship between key points and the key query distance is integral to this robustness. Thank you for listening. For more analysis and experiments, please refer to our paper or the code released on GitHub. Thank you.